Let's begin by exploring what an algorithm really is. Imagine one of our distant ancestors, inspired by watching his grandmother bake bread, decides to try it himself. He doesn't know the steps, so he experiments, hoping for a good result. This trial and error approach is familiar to all of us when we face new problems, but true bakers don't reinvent the recipe each time. They follow a set process, ensuring consistent results. This recipe, passed down through generations, is more than just tradition, it's an algorithm. An algorithm is a procedure that helps us solve problems without having to invent a new solution every time. From cooking and knitting to fishing and farming, humans have always created, shared, and improved algorithms. These step-by-step methods reduce uncertainty and allow anyone, even those without special talent, to achieve reliable outcomes. Algorithms aren't limited to recipes or physical tasks. They also solve problems involving symbols like numbers and letters. For example, searching for a word in a dictionary uses a specific algorithm. Open the book in the middle, compare your word to the one you find, and decide which half to search next. This process repeats until you find the word. These are called symbolic algorithms, and they're essential in mathematics and computer science. In fact, the concept of algorithms is as old as writing itself. Ancient scribes used algorithms for addition and multiplication to keep records. Mathematicians like Euclid developed algorithms to solve problems, such as finding the greatest common divisor of two numbers. Over time, the word algorithm evolved from the name of the Persian mathematician Al-Khwarizmi, whose work influenced both language and science. Algorithms can be described in many ways, as text, diagrams, or even through actions. For instance, Google Maps provides both a visual route and step-by-step directions to get from the Louvre to the Eiffel Tower. The same algorithm can be expressed differently depending on the audience, detailed for tourists, brief for locals. This flexibility shows that algorithms exist independently of language. Even ants use algorithms. When searching for food, scout ants wander randomly until they find a source, then leave pheromone trails for others to follow. Over time, the shortest path becomes the most popular, thanks to the accumulation of pheromones. Humans, however, strive to describe, memorize, and improve algorithms, even if we sometimes use them without being able to explain how they work, like recognizing a dog from a cat at a glance. At their core, algorithms are built from a few basic structures: assignment, setting a value; sequence, doing things in order; loops, repeating actions while a condition holds; and selection, choosing actions based on conditions. These simple building blocks can create incredibly complex solutions, much like how a few chemical elements combine to form millions of molecules. In practice, we rarely build algorithms from scratch. Instead, we often use existing algorithms as components in new ones, treating them as single steps within a larger process. For example, to get from the Picasso Museum to the Eiffel Tower, you might first go to the Louvre and then follow the previously described route. This modularity makes algorithms powerful and adaptable. There are many algorithmic techniques, each suited to different types of problems. Divide and conquer breaks a problem into smaller parts, solves each, and combines the results, like sorting mail by neighborhood, then by building, then by apartment. Generate and test lists all possible solutions and checks each one, which works for small problems but becomes impractical as complexity grows. Greedy algorithms make the best immediate choice at each step, aiming for a good solution quickly, though not always the best one. Randomization, as seen in Monte Carlo methods, uses chance to explore solutions, like throwing darts at a shape to estimate its area. These techniques show the creativity and diversity in algorithm design. Finally, let's look at algorithms that learn. Just as a baker improves with practice, some algorithms get better by repeating tasks and learning from outcomes. Recommendation systems on music, video, and book platforms analyze user choices to suggest new content. These systems don't need to understand the history of music, they simply find patterns in user behavior. More advanced learning algorithms, called deep learning algorithms, can recognize objects and images by first detecting simple shapes and gradually building up to complex features. This process mimics how children learn language or recognize objects, often without being able to explain their reasoning. Deep learning has enabled computers to master complex games like Go, sometimes even surpassing the best human players.